Hello friends, I welcome you to this channel, Learning Physics with IBM. And today, from the request of many of my students, I have decided to record another unit of physics paper 4. And I have decided to record quantum physics, solved past paper questions. This is physics 9702, paper 4. That is advanced structured questions. Of course, just to give you a small background, the study of quantum physics starts with Max Planck in 1900. Max Planck's paper on black body radiation is now the origin of quantum physics. Max Planck observed that the energy emitted by electromagnetic radiations was always quantized. In other words, the energy always existed in specific small amounts. That is according to Max Planck. Later on in 1905, Albert Einstein then extended Max Planck's paper, Max Planck's theory, Max Planck's observation, and he extended it to light. And Albert Einstein concluded that light is emitted in those small packets. It travels through space in those small packets and is absorbed by other objects in the same small packets. So we concluded that energy of electromagnetic radiations is always quantized. In other words, it comes in smaller packets. That is actually what we call quantum physics. The energy of electromagnetic radiations is always existing in small packets. That is, we say it is quantized. So without wasting any time, because I'm not teaching quantum physics now, I just want to take you through solve the past paper questions. I'll immediately go to our document, which has past paper questions that I expect that you have already downloaded. You have it in a printed copy so that using it becomes easy. But before we go to that, I want you to note that we shall be seeing a few of these concepts. To be specific, in this unit, I will discuss questions about photon energy, that is the energy of a photon, and questions will be about photoelectric emission or photoelectric effect. Questions will be about the wave-particle duality, that is light existing as a wave and at the same time as a particle, or electromagnetic radiation existing as a wave, or being explained as being made up of particles. We shall also see momentum of a photon, and lastly, the questions will be about electron energy levels. Remember, electron energy levels are going to be said to be quantized. In other words, electrons have specific energy levels, as you might have seen in your class of quantum physics. Here we are just going to concentrate on the past paper questions to see how these questions are actually examined. So expect questions about photon energy, photoelectric emission, the wave-particle duality, momentum of a photon, and electron energy levels. Straight away, let's go to the past paper questions. Here we are on quantum physics. Quantum physics, you can call it quantum mechanics. So we have started the questions. Without wasting much time, let us start the questions. So I will select my pen. Number 1. With reference to the photoelectric effect, state what is meant by work function. State what is meant by work function. Of course, work function, from the lessons you have had with your teacher, you must have used the letter phi for work function, and it must have been h f naught or hc divided by lambda naught. F naught was threshold frequency, lambda naught was threshold wavelength. So the work function is that minimum energy of a photon or minimum energy of electromagnetic radiation which is required to remove an electron from a metal surface. If the energy of the photon or energy of electromagnetic radiation is below the work function, then no electron can be emitted. The energy should be equal to work function or above the work function for an electron to be released from a metal surface. So the work function is the minimum energy of a photon or of electromagnetic radiation required to release or to remove an electron from a metal surface. The minimum energy of electromagnetic radiation, or you can say minimum energy of a photon, because after all, photons are electromagnetic radiations. The minimum energy of electromagnetic radiation required to remove an electron from a metal surface is what we call the work function. That minimum energy of electromagnetic radiation below which no electron is emitted from a surface or no electron is removed from a surface is what we call the work function. That energy of electromagnetic radiation below which no electron can be removed from a metal surface is what we call the work function. The work function energy of a clean metal surface is given as that, so that is phi. Electromagnetic radiation of wavelength 290 nanometers is incident on the metal surface. The metal is in a vacuum. Calculate the photon energy. So energy of a photon, I'll call it E, is equal to h f according to Albert Einstein's equation. So this is hc divided by lambda, because remember speed of a wave is equal to lambda times f. That's how it becomes hc over lambda. I just make f the subject, it will be c over lambda. So I just substitute directly because I know h is Planck's constant, which is 6.63 times 10 power negative 34, then times speed of light, which is 3 times 10 power 8, divided by the wavelength is 280 nanometers, which is 280 times 10 power negative 9. So I press my calculator. So from my calculator, this is 7.1 times 10 power negative 19. You can also check. 7.1 times 10 power negative 19. I want to remind you to desist writing any answer which is not exact to less than 2 significant figures. If the answer is not exact, write at least 2 significant figures, at least, not less than 2. Part 2, calculate the maximum speed Vmax of the electrons emitted from the surface. So this is the photon energy. Remember, the work function has been given. So if this is the photon energy and the work function has been given as that, what is the kinetic energy? According to Albert Einstein's equation, energy of a photon is equal to the work function phi plus the maximum kinetic energy, Emax. The energy of a photon we have calculated it as 7.1 times 10 power negative 19. The work function has been given as 5.5 times 10 power negative 19 plus the maximum kinetic energy is given as a half m times the maximum speed Vmax squared. So we want to find the maximum speed. So we just subtract and make V the subject here. So the maximum speed V, I'm just going to make Vmax the subject, will be equal to the square root of, I'm subtracting these energies, so that is 7, but I will multiply this by 2, so it will be 2 times, in 2 brackets, I'll just say in 2 brackets, 7.1 minus 5.5, and this is times 10 power negative 19. So that is the difference in energy, energy of the photon minus the work function, then times 2, because I'm making V max the subject, divide by the mass. These are electrons, so the mass is the mass of an electron, 9.11 times 10 power negative 31. So I press my calculator. If you're not a math student, you can do this step by step. You take this one the other side, you subtract. You multiply by 2. You divide by the mass m of an electron, then you find a square root. If you're a math student, this is direct. So from my calculator, Vmax is 5.9 times 10 power 5. 5.9 times 10 power 5 meters per second. So that is the maximum speed. Explain why most of the emitted electrons will have speed lower than maximum. Remember, not all electrons in atoms of the metal surface reside on the surface. Some electrons reside below the surface. Remember, the energy of the photon is the one to bring those electrons below the surface to the surface first. And then when they are now at the surface, the excess energy is now to give them kinetic energy. So since most of the electrons do not reside at the surface, they will have energy less than the maximum kinetic energy. It is only the surface electrons which have maximum kinetic energy. So we can say most electrons are below the surface, and the energy is required to bring them to the surface. Since it is just 1 Mach, most electrons are below the surface. Most electrons are below the surface, and energy is required to bring the electron to the surface. Most electrons are below the surface, and energy is required to bring the electron to the surface. That's why the energy of these electrons, which we got from below the surface, will be less than the maximum, will give less than the maximum kinetic speed. Because some energy is used to bring them to the surface, so what remains is relatively lower than the maximum kinetic energy. Okay. The electromagnetic radiation incident on the metal surface may change in intensity or in frequency. Complete the figure by inserting either increases or decreases or no change to describe the effects of the changes shown on the maximum speed and on the rate of emission of electrons. So the rate of emission, that is the number of electrons emitted per unit time. The maximum speed depends on the maximum kinetic energy, and maximum kinetic energy depends on the energy of the photons. So energy of the photon, this is energy of the photon is equal to the work function plus the maximum kinetic energy, Emax, or I can say HF is equal to HF naught plus a half m Vmax squared. So let's start. If we reduce the intensity at a constant frequency is not changing, the intensity is changing. So if the frequency is not changing, then the energy of the electrons is not affected. So here there is no change. Maximum speed of electrons, no change. There is no change. But if the intensity is reduced at a constant frequency, what happens to the rate of emission? Remember, intensity is the number of particles emitted, is the number of photons per unit time, the number of electrons per unit time. So if the intensity is reduced, what happens to the rate of emission? Reduced intensity at a constant frequency, it means there are now fewer photons incident on the surface. If there are fewer photons incident on the surface, they will cause fewer electrons to be ejected, because remember, this was a one-to-one interaction. One photon only knocks out one electron. So if the number of photons is reduced, then it means the number of electrons emitted also decreases. So the answer here will be decreases. Increased frequency at a constant intensity. Increasing frequency, it means the photon energy has increased, so the maximum kinetic energy of electrons increases. So this one is obvious. This one increases. And how about the rate of emission? The intensity is constant, but the frequency has been increased. Intensity is equal to power per unit area. Power is energy over time, so this will be energy over T times A. And the energy is HF, but since we have a number of photons, so energy will be N times HF divided by T times A. Intensity is equal to that. Frequency is increased. Frequency has been increased, but intensity is not increasing. You notice that the number of photons per unit area, per unit time, is inversely proportional to frequency, as long as the intensity does not change. The number of photons, which is the rate of emission of electrons, the number of photons incident on the area, is inversely proportional to the frequency if the intensity is constant. Therefore, what does that mean? If the intensity does not change and we increase the frequency, it means there will be fewer photons incident on a given area. And although they have higher frequency, they are fewer. And if they are fewer, they will cause only a few electrons to leave the surface. Therefore, the rate of emission also decreases. Okay, next. So I'll be so slow on this on quantum. I want to write it very well and give more explanation where possible. Electromagnetic radiation of a single constant frequency is incident on a metal surface. This causes an electron to be emitted. Explain why the maximum kinetic energy of the electron is independent of the intensity. Why is the maximum kinetic energy independent of the intensity? Of course, remember, intensity determines the number of photons per unit time, but it does not determine the energy of a photon. It just determines the number of photons incident on the surface per unit time. It does not determine the energy of the photon. Remember, maximum kinetic energy depends on frequency. The maximum kinetic energy depends on frequency, which frequency depends on the energy of the photon. So kinetic energy of the electron depends on the energy of the photon rather than the intensity. So since there are 3 marks, we can give more details. Intensity determines the number of photons per unit time. The intensity determines the number of photons per unit time, but it does not determine the energy. It does not determine the energy of a photon. So intensity does not determine energy of a photon. It is the frequency which determines the energy of the photon. Does not determine energy of a photon. It is the frequency which determines energy of a photon. It is the frequency which determines energy of a photon. It is the frequency which determines the energy of a photon. And kinetic energy of the electron depends on the energy of the photon. Kinetic energy of the electron depends on the energy of the photon. So kinetic energy depends on the energy of the photon, but intensity does not determine the energy of the photon, it just determines the number of photons. That's why the maximum kinetic energy is independent of the intensity. Ultraviolet radiation of wavelength 250 nanometers is incident on the surface of a sheet of zinc. The maximum kinetic energy of the emitted electrons is 1.4 electron volts. Determine in electron volts the energy of a photon of the ultraviolet radiation. So energy of a photon is equal to HF, which is the same as Hc divided by lambda, where H is 6.63 times 10 power negative 34 times C, which is 3 times 10 power 8, divided by the wavelength, which is 250 times 10 power negative 9. So I press my calculator. So from my calculator, I'm getting 7.96 times 10 power negative 19, and this is in joules. The answer in electron volts, so I'm going to divide this by 1.6 times 10 power negative 19. So this will be the same as 7.96 times 10 power negative 19 divided by 1.6 times 10 power negative 19. 7.96 divided by 1.6. So this is 4.98. This is 4.975, which is approximately 5.0. Remember, I avoid writing answers to less than two significant figures. So it is approximately 5.0 to two significant figures, or 5.98 to three significant figures, electron volts. Part 2, determine in electron volts still the work function energy of the surface. They have told us the maximum kinetic energy is 1.4 electron volts. And we have seen the photon energy is 5.0 electron volts. Then work function. According to Albert Einstein's equation, energy of the photon, part of it becomes the work function to set the electron free, and part of it becomes the maximum kinetic energy. So the energy of the photon is 5.0, the work function is 1.4 plus, no, not the work function, the kinetic energy. The work function is what we want to find, the kinetic energy is 1.4. So you notice that work function is going to be 5.0 minus 1.4, which is obviously 3.6 electron volts. Okay. State what is meant by a photon. Of course, a photon is now easy. This question will appear over 100 times in this unit of quantum physics. I will be defining it so that it becomes part of you every time. I will be defining it. So a photon is a packet of energy, or a quantum of energy of electromagnetic radiation. So a photon is a packet of energy or you can call it a quantum of energy if it is 1. A quantum, because according to Max Planck, energy emitted by a black body was existing in small packets. And Albert Einstein verified or gave his explanation, his extension, and said light is produced in small packets. It is also absorbed in small packets, and there is evidence. So a photon is a packet of energy, or we can call it a quantum. The word quantum comes from quanta, which means how much, what specific amount. So a quantum of energy, of electromagnetic radiation. And remember, the energy of a photon, the energy of a photon is equal to Planck's constant multiplied by frequency. Okay. A stationary nucleus of samarium emits a gamma ray photon of energy 0.57. Okay. Determine for one gamma ray photon its wavelength. For one gamma ray photon, determine the wavelength. So we just know energy is equal to hc divided by wavelength. And we want the wavelength, so this implies that the wavelength is going to be hc over energy. H is 6.63 times 10 power negative 34 Planck's constant. Then C is 3 times 10 power 8. Divide by, we are going to divide this by the energy. The energy is given as 0.57 mega electron volts. Remember, mega, if 1 electron volt is the same as 1.6 times 10 power negative 19 joules, then mega, we multiply this side by 6, 10 power 6, even the other side by 10 power 6. So 1 mega electron volts is the same as 1.6 times 10 power negative 13 joules. So the energy will be therefore 0.57 times 10 power 6 times 1.6 times 10 power negative 19. Or I removed the mega by 10 power 6, then electron volts, that is 1.6 times 10 power negative 19. Or I can just replace it with times 10 power negative 13 without adding 10 power 6 here. So I press my calculator. So from my calculator, this is 2.2 times 10 power negative 12. 2.2 times 10 power negative 12. That is the wavelength. Then its momentum, we know that momentum is equal to h over lambda, or momentum is equal to the energy over c according to Albert Einstein. Albert Einstein had already established that the momentum of a photon is related to its energy by that equation, or the momentum can now be h over lambda, because remember, if it is a photon, its energy is hf, so this will be hf over c, but remember f is c over lambda, so this ends up, this will be hc multiplied by, where there is f, I put c over lambda, which takes us back to that. So whichever we use will give us the momentum. So the momentum is going to be equal to 6.63 times 10 power negative 34 divided by the wavelength. I'm using the one of wavelength, which is 2.2 times 10 power negative 12. So I press my calculator. You can always press the calculator to check because I'm human, I'm bound to make mistakes. So from my calculator, this is 3.0 times 10 power negative 22 Newton seconds as the momentum P. Use your answer in B Roman 2. Using your answer to B Roman 2, determine the speed of samarium nucleus after emission of the photon. So first of all, the speed, of course, momentum now is m times v. Momentum will be m times v. Of course, after emission of the photon, samarium is going to recoil for momentum to be conserved. If momentum is conserved, the momentum of the photon should be equal to the momentum of samarium, but in opposite directions, so that the total momentum is zero because samarium was initially stationary. Total initial momentum was zero. Total momentum after should also be zero. And how will it be zero? When the photon is emitted to the right, samarium must recoil to the left. So we can begin by finding the mass of samarium. So mass, because momentum will be mass times velocity. So the mass of SM 157, of course, mass is going to be nuclear number is in U, so we just change it to kilograms. So this will be 157, that is U, 157 U. And 1 U is 1.66 times 10 power negative 27 kilograms. So this will be 157 times 1.66 times 10 power negative 27. Now it is in kilograms. So that is the mass. That is the mass. Okay. So from momentum equals to mass times velocity, I know that the momentum will be the same but in opposite directions. So the recoil speed, that is the speed with which the samarium moves backwards. The recoil speed is going to be now momentum divided by the mass. So that will be 3.0 times 10 power negative 22 divided by the mass, which is 157 times 1.66 times 10 power negative 27. So I press my calculator. So from my calculator, the speed is 1.2 times 10 power 3. Always have a calculator and check. The more you learn to use your calculator, the better. By reference to your answer in C Roman 1, explain quantitatively why the speed of samarium 157 nucleus may be assumed to be negligible compared with the speed of the photon. Note that the speed of the photon is actually the speed of light, which is 3 times 10 power 8 meters per second. Explain quantitative, that is quoting values. When it is quantitatively, we quote some values. Why the speed of the samarium nucleus may be assumed to be negligible compared with the speed of the photon. So you notice that the speed was 1.2 times 10 power 3 meters per second. This one is much less, is much smaller, this is very important. Emphasis is very important here, is much less than 3.0 times 10 power 8 meters per second, because this is the speed of the photon. So that's what is expected. Or you can say 3.0 times 10 power 8 meters per second is much greater than 1.2 times 10 power 3. So emphasis is very important. With reference to the photoelectric effect or photoelectric emission, state what is meant by threshold frequency. there is a certain minimum frequency below which no photoelectric emission is going to occur. There is a certain frequency below which no release of electrons can occur, and that frequency is what you call the threshold frequency in your quantum physics classes. Okay, so the minimum frequency of electromagnetic radiation, or minimum frequency of a photon. The minimum frequency of electromagnetic radiation, or the minimum frequency of a photon, required to cause emission of electrons, or below which no photoelectric emission occurs. The minimum frequency of electromagnetic radiation required to cause let me just say the minimum frequency of electromagnetic radiation below which no emission of electrons occurs from a surface. If the energy of a photon is less, if the frequency of a photon is less than the threshold frequency, it will not cause an electron to leave a surface. That is the threshold frequency. Okay. Electromagnetic radiation of wavelength lambda is incident on a metal surface. Electrons of maximum kinetic energy, Emax, are emitted. On the figure, sketch the variation with 1 over lambda of Emax. Of course, from Einstein's photoelectric equation, the energy of the photon is equal to the work function plus Emax. The energy of the photon is going to be hc over lambda. The work function is hc over threshold wavelength plus Emax. We are plotting a graph of Emax on the y-axis against 1 over lambda. You see that there is an intercept. There is an intercept. Let's check. If Emax is 0, 1 over lambda is equal to 1 over lambda naught. That means the graph should touch the x-axis. For Emax equals to 0, this is going to be 1 over lambda naught. The graph touches the x-axis. And now you notice that Emax, for other points, Emax is directly proportional to 1 over lambda. Emax is directly proportional to 1 over lambda, so that is a straight line, which has an x-intercept at a certain value. So I will draw a straight line through 1 over lambda naught. So that is a straight line. Emax increases as 1 over lambda increases. That is a straight line. Note that Emax is directly proportional to 1 over lambda, but is inversely proportional to lambda itself. But this is a graph of Emax against 1 over lambda. Okay, state an equation relating the gradient of the graph drawn to the Planck constant, h. Explain your symbols. So you are going to notice if we plot Emax equals to hc times 1 over lambda plus hc over lambda naught. Y is equal to mx plus c. So you see that the gradient m is equal to hc. So we just simply say gradient the gradient is equal to hc, where c is the speed of light. H is defined, so c is the speed of light. So c is the speed of light. Okay, explaining why for any particular wavelength of electromagnetic radiation, most of the electrons are emitted with kinetic energy less than the maximum value. I have already mentioned that it is the surface electrons which have maximum kinetic energy, because for them, they are almost free. The electrons below the surface need energy to bring them to the surface before they become now free to move away. So if the same photon is to knock out an electron on the surface, and a similar photon is to bring an electron to the surface before surplus energy is given to it to move away, then the electron which came from the surface will have smaller kinetic energy. So since there are two marks, we shall start by saying an electron emitted from the surface has maximum kinetic energy. An electron emitted from the surface has maximum kinetic energy. For electrons below the surface, below the surface, energy is required to bring them to the surface. For electrons below the surface, energy is required to bring them to the surface. So let us say a photon has a certain amount of energy, let's say 2 times 10 power negative 10 joules. Let's say photon has that. If this photon is absorbed by an electron on the surface, it means almost all this energy becomes kinetic. But if this photon interacts with an electron below the surface, part of this is to bring the electron to the surface. So what remains becomes smaller. So that electron will now have smaller kinetic energy. Okay. For a particular wavelength, light of a particular wavelength is incident on a metal surface and gives rise to a photoelectric current. That is emission of electrons. Number of electrons emitted per unit time, that is the photocurrent. The wavelength is reduced, so lambda is reduced. The intensity of the light is kept constant. Intensity is not changing, the wavelength is reduced. State and explain the effect, if any, on the photoelectric current. That is, the effect on the number of electrons emitted per unit time. The wavelength is reduced, but the intensity is not changed. Of course, photocurrent, that is the number of electrons emitted per unit time. The number of electrons emitted depends on the number of photons incident on the surface. The number of photons incident on the surface is controlled by the intensity. If the intensity is constant, it means the same number of photons are incident on the surface. But the wavelength is reduced, remember? And if the wavelength is reduced, it is now going to affect again the number of electrons arriving on the surface per unit time. Because remember, intensity is power per unit area, which is energy over T times area, which is going to be the number of photons times the energy of each photon divided by T times the area. that is NHF. Now, if remember F is inversely proportional to the wavelength, so it means intensity is going to be equal to NH C over T A times lambda. The wavelength has been reduced. If the wavelength has reduced, is equivalent to increasing the frequency. It means the frequency has been increased. If the intensity does not change, now I want you to note this very carefully. If the intensity does not change, it means N over T is inversely proportional to frequency. N over T is inversely proportional to frequency. So if the frequency has been increased, then it means N over T must decrease if the intensity is not changing. If the intensity does not change, then we are going to have fewer number of photons arriving on the surface per unit time if the intensity is not changed, but the wavelength is decreased or the frequency is increased. So each photon now have more energy, but we can only have a few photons incident on a given area per unit time. So each photon will now have more energy because the frequency has increased. Each photon will now have more energy. Each photon will now have more energy, so there will now be fewer photons per unit time. So there will be fewer photons per unit time. Thus, since there are now fewer photons per unit time arriving on the surface, thus fewer electrons emitted per unit time. Because remember, each photon causes one electron to be emitted. Thus, fewer electrons emitted per unit time. And if there are fewer electrons emitted per unit time, remember the number of electrons per unit time is the photocurrent, hence less current. So there will be less current. Okay. State what is meant by a photon. A photon is a packet of energy of electromagnetic radiation. Packet of energy of electromagnetic radiation. That is a photon, and the energy is HF. Packet of energy of electromagnetic radiation, and the energy is HF. Light in a beam has a continuous spectrum that lies within the visible region. The photons of light have energies ranging from 1.60 electron volts to 2.6 electron volts. The beam passes through some hydrogen gas, then passes through a diffraction grating, and an absorption spectrum is observed. All of the light absorbed by hydrogen is re-emitted. All the light is re-emitted. Explain why darker lines are still observed in the absorption spectrum. So a beam is passing through hydrogen. We know that some photons are absorbed, but all photons are now again re-emitted, but still we are not seeing them on the other side. Why do we have darker lines? Of course, during absorption, and re-emission. When the photons are re-emitted, they are re-emitted in all directions, and you may find that only a small part of the re-emitted light is in the same direction as the original beam. Those photons which are not re-emitted in the same direction as the original beam will not be seen on the screen. Therefore, the points correspond to those photons will now be dark lines. Okay. So light is re-emitted. Light is re-emitted randomly in all directions. Light is re-emitted in all directions, which means also only a part of the re-emitted light only a part of the re-emitted light is in the direction of the beam. Light is re-emitted in all directions, so only a part of the re-emitted light is in the direction of the beam. So the other part which is not in the direction of the beam will appear as dark lines on the screen or in the spectrum. Some of the energy levels of an electron in hydrogen atom are illustrated here. Those are the energy levels of an electron. Of course, remember negative 13.6 is the ground state, the lowest energy possible for an electron in a hydrogen atom. The dark lines in the absorption spectrum are the result of electron transition between energy levels. On the figure, draw arrows to show the initial electron transition between energy levels that could give rise to dark lines in the absorption spectrum. So they have told us light is in the range. The photons of light have energies ranging from 1.6 electron volts to 2.60 electron volts. And they're asking us to find on the figure to draw arrows to show the initial electron transitions between energy levels that could give rise to dark lines in the absorption spectrum. So we have to check the energies. Let's check. Just get my calculator. Light of energies ranging from 1.6 electron volts to 2.6 electron volts. I'll try to add 1.6 to 3.1.6, 3.4 plus 1.6. Sorry, negative 3.4 plus 1.6. That's negative 1.8. That may not be possible. Or alternatively, I can just subtract to see the energies in that range. There's no problem. Let's check. Let's check the first transition and see if it is possible. Let's check this one. That is negative 0.54 minus negative 13.6. We get 13.0306. It is not in this range, so this transition is not possible. Let's check another one. Of course, you are doing this with the pencil. Transition from again the first one to the second one, that is negative 0. We have checked negative 0.54 minus negative 13.60, and this was 13.6. 0.06 electron volts. That is outside the range. The range is from 1.6 to 2.6, I guess. 1.6 to 2.6, this is the range. So the first one is not possible. Let's check the second one, 0.54 minus negative 3.40. Let's check that one. Negative 0.54 minus negative 3.4. So this gives us 2.86, which is outside the range. That is not possible. We can check another one. So this transition is not possible. Wait to draw. We can now check from negative 0.54 to negative 1.51. Negative 0.54 minus negative 1.51. So this gives me 0.97, which is in the range. So this is possible. So I will draw that one. I can have this one. Then I'll check the second one. I can check negative 0.54, negative 0.54 minus negative 0.85. Negative 0.54 minus negative 0.85. So this is 0.31. That is within the range. No, it is outside the range. Even this one is outside the range. Sorry. 0.97. No, that is outside the range. So this is not possible. This is also not possible. It is outside the range. Okay, so I'm done with that one. I will now move to 0.85. Negative 0.85 minus negative 13.60. I'll just say 13.6 minus 0.85. That is 12.75. It is outside the range. Negative 0.85 minus negative 3.40. 3.4 minus 0.85. It is 2.55. 2.55 is in the range. So I will have a transition from here up to there. That is 1. 2.55 is in the range because the range is to 1.6 to 2.6. Then I will say a negative again 0.585 minus negative 1.51. In other words, 1.51 minus 1.51 minus 0.85. That is 0.66. It is outside the range. So I am done with that one. I can now move to 1.51. So I have negative 1.51 minus the ground state, negative 13.60. That is obviously outside the range. It is very big. Negative 1.51 minus negative 3.40. So 3.40 minus 1.51. That is 1.89. This is 1.89, which is within the range. 1.89, which is within the range, so that one is fine. Transition from this one to this one is possible because it is giving us an energy in the range. So we are done with 1.51. Let's now check. Of course, we can't even check negative 3.4 to negative 13.6 because the difference is very large. So there are only two transitions which are possible. We have from negative 0.85 to 3.4 and negative 1.51 to 3.4. So those are the arrows that we're supposed to draw. Those are the arrows you're supposed to draw. Okay. Calculate the shortest wavelength of the light in the beam. The shortest wavelength of the light in the beam. Okay, so because the wavelengths range from 1.6 to 2.6, then it means the highest, the energies range from 1.6 to 2.6. The one with the highest energy has the shortest wavelength. So energy is equal to h c over lambda. So the wavelength is going to be h c over energy, which is 6.63 times 10 power negative 34 times 3 times 10 power 8. Divide by the highest energy, which is 2.6 electron volts. So that will be times 1.6 times 10 power negative 19 to change it to joules. So I press my calculator. So from my calculator, I am getting 4.8 times 10 power negative 7. 4.8 times 10 power negative 7. Okay, next, state what is meant by photon. Now you are familiar with the photon. That is a packet of energy. A packet of energy of electromagnetic radiation. And the energy, we know that the energy is H times F. Calculate the energy in electron volts of a photon of light of that wavelength. So we know energy is H C over lambda. So this is going to be 6.63 times 10 power negative 34 times 3 times 10 power 8 divided by 540 times 10 power negative 9. So I'm pressing my calculator. So this is giving me 3.68 times 10 power negative 19. That is in joules. I'm going to convert it to electron volts. So I divide by 1.6 times 10 power negative 19. So from my calculator, this is 2.3 electron volts. Okay. By reference to the photoelectric effect, explain what is meant by work function. We have already defined work function. Now we are familiar with this. The minimum energy of electromagnetic radiation required to remove an electron from a metal surface. The minimum energy of electromagnetic radiation below which there will be no emission of electrons from a metal surface. So minimum energy of electromagnetic radiation required to remove an electron from a surface. The minimum energy of electromagnetic radiation required to remove an electron from a surface or from a metal surface. Let me be specific, from a metal surface. That is the work function. In an experiment, electromagnetic radiation of frequency F is incident on a metal surface. The results in the figure show the variation with the frequency F of the maximum kinetic energy of electrons emitted from the surface. So we have a graph. The graph is always similar in shape. It is always a straight line. So this is a graph of maximum kinetic energy against the frequency, as we can see. Maybe it will be necessary for us to prolong this line. So I'm going to prolong this line so that it touches the x-axis. Maybe it may be necessary. I don't know. We may need to find F naught, so I'll prolong this line. So when I prolong it, it is touching 5.4. I guess. Is it 5.45? Yes. The scale here is 0.5 divided by 10, 0.05. So this is 5.45 because there are two small squares which make 0.1. So this reading here, the reading there is 5.45 times 10 power 14 hertz. And this is going to be the threshold frequency, the frequency for which maximum kinetic energy is 0. That is going to be the threshold frequency. So let us see now the questions. Determine the work function, energy in joules of the metal used in the experiment. So that is now very easy. Energy of the photon is given as HF, which is equal to the work function plus the maximum kinetic energy. We notice that when Emax is 0, the energy is, when Emax is equal to 0, it means that the work function is equal to H times F. We just look for that point where Emax is 0, and it will give us the threshold frequency F naught. From the graph, we notice that F naught is 5.45 times 10 power 14 hertz. So the work function phi is going to be H, which is 6.63 times 10 power negative 34 times F naught, which is 5.45 times 10 power 14 hertz. So I press my calculator to find the work function. And from my calculator, the work function is 3.6 times 10 power negative 19 joules. The work function energy in electron volts for some metals is given in the table. They have given us tungsten, magnesium, and potassium. Determine the metal used in the experiment. Show your working. So we can determine the metal used in the experiment. We just convert that energy, that work function, to electron volts and see which of these is very close to it. So we shall have 3 energy is equal to 3.6 times 10 power negative 19, and I divide this by 1.6 times 10 power negative 19 to get the energy in electron volts. So 3.6 divided by 1.6. and I'm getting 2.25. 2.25, you notice that it must have been approximately potassium. I can go back and see if I can change the work function to more significant figures. Let's check. 6.63 exponent negative 34 times 5.45 exponent 14. So this is actually 3.613 times 10 power negative 15. I just want to see if I can arrive at 2.26. So let me see, 3.613 times 10 power negative 19 divided by 1.6 times 10 power negative 19 divided by 1.6 exponent negative 19. Yeah, so this one is giving me, when I use more exact values, this one is giving me 2.26. It is giving me 2.26. But this one is fine, 2.25 electron volts. We know that this is the nearest. So if you use more significant figures, you will arrive at it. So it is potassium. So it is potassium that is being used. The intensity of the electromagnetic radiation for one particular frequency in B is increased. State and explain the change, if any, in the maximum kinetic energy of the emitted electrons. Intensity is increased. Intensity does not affect kinetic energy. Kinetic energy depends on frequency. So state and explain. So we simply say kinetic energy depends kinetic energy depends on frequency, not intensity. Each photon has the same energy, so there is no change because the frequency is not changed for one particular frequency. So each photon has same energy. So there is no change. The rate of emission, that is the number of photons emitted. The intensity is increased. Of course, the rate of emission will also increase because intensity is the number of photons emitted per in time, which is the number of electrons emitted per in time. So that is the rate of emission. So there will be more photons per in time, so the rate of emission increases. There will be more photons. There will be more photons per in time. So the rate of emission increases. Rate of emission increases. A pi-zero meson is a subatomic particle. You remember a meson from AS, a particle which is made up of a quark and an antiquark. For example, up and anti-down, that is a meson. A stationary pi-zero meson which has mass, this is the mass of the pi meson, decays to form two gamma ray photons. The nuclear equation for this decay has been given. Remember, it is initially stationary, total momentum is 0. But it decays by emission of two gamma ray photons. Explain why the two gamma ray photons have the same energy. Of course, they must have the same energy because momentum must be conserved. Remember, momentum is going to be E over C. They must have the same energy to conserve momentum, and the momentum must be in opposite what? Directions. If the momentum is to be equal, the energy should be the same because C is a constant. It should be equal but opposite. Momentum should be equal but opposite for the two gamma ray photons. To conserve momentum, the momentum should be equal but opposite so that total momentum is 0. And momentum is depending on the energy, so the energy must be the same. So to conserve momentum, the momenta of photons are equal but opposite. Momenta is plural. The momenta of photons are equal but opposite. And since photons have the same momentum, they have the same energy. They have the same energy. Okay, so we have seen that to conserve momentum, the momenta of photons are equal but opposite. And I've showed you here that momentum is energy over C. If the momentum are equal but opposite, the energy is going to be the same. The energy is going to be the same. Determine for each gamma ray photon the energy in joules. So that is just for one gamma ray photon. So energy is equal to mc squared. Since we don't have the wavelength, I'll use energy equals to mc squared. Remember, the mass of the pi meson is what has become energy in form of gamma ray photons. The mass is what has become energy in form of gamma ray photons. This gave the energy of two photons is 2.4 times, the mass of the pi meson is 2.4 times 10 power negative 18, 28 kilograms. That mass gave two particles. So we are going to divide that mass by 2 to get the mass of one particle. So for one particle, the mass will be actually half of that, so it will be 1.2 times 10 power negative 28. If there are two particles, this mass is giving us two particles, and we want only one particle, so we just divide that mass by 2. Okay, so this is going to be equal to 1.2 times 10 power negative 28. Then I multiply this by 3 times 10 power 8, and this is squared. Or I can find the total mass and divide the total energy and divide it by 2. I can use 2.4 times 10 power negative 28, then I divide by 2. So from my calculator, this is 1.08 times 10 power negative 11. Then the wavelength, since I have the energy of one photon, the wavelength, remember, energy of a photon is also hc over lambda. So the wavelength is going to be 6.63 times 10 power negative 34 times 3 times 10 power 8 divided by the energy, which is 1.08 times 10 power negative 11. 1.08 times 10 power negative 11. So this is going to be 1.84 times 10 power negative 14 in meters. Then the momentum, of course, we know that momentum is energy over c, which is the same as h over lambda. So the momentum will be equal to the wavelength, which is will be equal to h, which is 6.63 times 10 power negative 34, divided by the wavelength, 1.84 times 10 power negative 14. So this is going to give me 3.6 times 10 power negative 20 as the momentum. You can also verify with your calculator. Experiments are conducted to investigate the photoelectric effect. It is found that on exposure of a metal surface to light, either electrons are emitted immediate, that is instantaneous nature, or they are not emitted at all. Suggest why this observation does not support a wave theory of light. Why doesn't this suggestion support wave theory of light? The wave theory suggests that there is no need for instantaneous emission. Even though photons have small amount of energy, the electron will absorb energy from different photons, and when the energy is enough, the electron will be ejected. But observations show that that does not happen. So for a wave theory, an electron can collect or accumulate energy. For a wave theory, for a wave theory, an electron, for the wave theory, if for a wave, an electron can collect, I'll put collect in quotes, can collect and accumulate. And accumulate energy continuously. Energy continuously, and will always be emitted at all frequencies after sufficiently long delay. After sufficiently long delay. So the wave theory says there is no need for emission to be instantaneous. The wave theory predicts that an electron will absorb photons of different photons, even though their energy is small. The electron will collect and accumulate enough energy for it to be emitted. So this can even take a longer period of time. Even though the photons have smaller energy, that is a smaller frequency, the electron can absorb many of them for over a long period of time, and when the energy is enough, the electron can now leave the metal surface. But observations show that that does not happen, so the wave theory that is now discarded. The photon theory that we are going to see, or the particle theory, actually now proves that as soon as light of enough frequency is incident on the metal surface, the electron is emitted. But even if you shine light for the whole day, as long as the photons have lower frequency or lower energy, no observation, no emission was observed. That is the photon theory, in contradiction with the wave theory. The wave theory You can shine light which is of lower frequency for a long period of time, and it predicts that the electron will collect energy over a long period of time and is ejected, but that does not happen. The photon theory verified that if you shine light of high frequency, emission is instantaneous. If you shine light of low frequency, even if you shine it for the whole day, there is no actual emission. Okay. Data for the wavelength of the radiation incident on the metal surface and the maximum kinetic energy of the emitted electrons are shown in the table here. Without any calculation suggests why no value of Ek for the radiation, there is no value of Ek for the wavelength of 650 nanometers. Why is it that there is no value for kinetic energy? Data for the wavelength of radiation incident on the metal surface and the maximum kinetic energy of the emitted electrons are shown here. Without any calculation suggests why no value is given for kinetic energy for radiation of wavelength 650 nanometers. Why do we think there may not be kinetic energy for the radiations of that wavelength? Note that there is a minimum frequency below which no photoelectric emission occurs. That was the threshold frequency. And therefore there is a maximum wavelength. If the frequency is minimum, the wavelength is maximum. Remember, C is equal to lambda times F, meaning that lambda is inversely, or F is inversely proportional to lambda. When F is maximum, lambda must be minimum. So it seems like there is a maximum wavelength, which we are going to call the threshold wavelength, above which no photoelectric emission occurs. So maybe lambda is longer than the threshold wavelength. Lambda is longer than the threshold wavelength. Longer than the threshold wavelength. And if lambda is longer than the threshold wavelength, there is no emission, so we can't talk about kinetic energy. Or we can say the frequency is below the threshold. Frequency is below the threshold frequency. The frequency of the electromagnetic radiation is below the threshold frequency. Or we can even say the photon energy is less than the work function. Or it could be that the photon energy is less than the work function. So there is no emission if the photon energy is less than the work function. Okay, use data from the figure to determine the work function energy of the surface. So from the figure we have 240, the kinetic energy has been given there. Okay, so from the table we know that the energy of the electron of the photon is hc over lambda, which is equal to the work function plus the maximum kinetic energy Emax. So we are just going to substitute. H is 6.63 times 10 power negative 34 times 3 times 10 power 8 divided by the wavelength has been given as 240. The corresponding wavelength is 240. So that is 240 times 10 power negative 9, because it's given in nanometers. Then this should be equal to the work function phi plus the maximum kinetic energy which is 4.44. They gave us 4.44 times 10 power negative 19. 4.44 times 10 power negative 19 joules. So I make phi the subject, and I'll just divide on the left, subtract 4.44, and find the answer. So this is 3.8. Phi is 3.85 times 10 power negative 19 joules. 3.85 times 10 power negative 19 joules. So this is going, it is approximately 3.9 for some people who press the right and rounded off. So this is 3.85 times 10 power negative 19 joules as the work function. Radiation of wavelength 240 nanometers gives rise to a maximum photoelectric current I. The intensity of the incident radiation is maintained constant. So I is intensity of the incident radiation is constant. It gives maximum photoelectric current. The wavelength is now reduced. Remember, lambda is reduced. It means F is increased. And if intensity is not changed, remember intensity is equal to power per unit area, and power is energy over time per unit area. That is NHF over T times A. If intensity does not change, it is a constant, and frequency is increased, by all means, the number of photons incident on the same area reduces. If intensity is not changing and the frequency is increased because the wavelength is decreased, the number of photons per unit time arriving is decreased. So let's see, state and explain the effect of this change on maximum kinetic energy of photoelectrons. Of course, maximum kinetic energy depends on frequency. The intensity is maintained constant, the wavelength is now decreased, meaning the frequency is increased. So photon energy is larger. Photon energy is larger. Photon energy is larger. What does that mean? So maximum kinetic energy is larger. So maximum kinetic energy is larger. The maximum kinetic energy is larger because remember energy of the photon is equal to phi work function plus maximum kinetic energy. Energy of the photon is HF, which is equal to phi plus Emax. So if the frequency has been increased, Emax has been increased. Then the maximum photoelectric current I, that is now intensity, number of electrons emitted per unit time. Intensity is not changing. How many electrons are emitted per unit time? The intensity of the radiation is remaining constant. If the intensity of the radiation is remaining constant, remember it means we can now have fewer photons per incident on the area per unit time because they will now have more energy. So higher photon energy means fewer photons per unit time. Higher, because the wavelength is reduced, the frequency is increased. That means energy is higher. Higher photon energy means fewer photons per unit time. Means fewer fewer photons per unit time. Means fewer photons per unit time. So maximum current, maximum photocurrent is smaller. This is the most confusing question here. They say the intensity of the incident radiation is maintained constant. What happens to the photoelectric current? Remember, the photoelectric current is the number of electrons emitted per unit time. If the intensity of the incident radiation remains constant, yet their photon energy has been increased, it means now we can only have fewer photons incident on a given surface per unit time. From this expression here, N over T becomes smaller. Fewer photons will now be incident on a given area per unit time. State what is meant by the de Broglie wavelength, that is the wavelength of a moving particle, wavelength associated with a moving particle. Wavelength associated with a moving particle. The wavelength associated with a moving particle. An electron is accelerated in a vacuum from rest through a potential difference of 850 volts. Show that the final momentum of the electron is 1.6 times 10 power negative 34 Newton seconds. So an electron is accelerated through a vacuum from rest without PD. We can find the energy of the electron. Energy of the electron is going to simply be E times V. Energy of the electron is going to be E times V. So which is going to be 850. That is the accelerating PD, 850 times the charge of the electron, 1.6 times 10 power negative 19 joules. That is the energy of the electron. Show that the final momentum of the electron is given by that. So we also know that momentum is m times v, but energy is going to be a half mv squared, which is going to be E times V. So I multiply both sides by 2, both sides by m. So I have m squared, V squared is equal to twice E V times 1m. I've multiplied both sides by m and both sides by 2. This side now you know that momentum is mass times velocity. So this side is momentum squared. So you notice that therefore momentum is going to be the square root of 2ev times m divided by 2ev times m divided by, actually it is 2ev times m because I'm finding the square root. Yes, this is momentum squared equals 2ev times m. So remember ev is that one, so I just substitute. This will be the square root of 2 times E, which is 1.6 times 10 power negative 19 times V, which is 850 times M, 850 times M, which is 9.11 times 10 power negative 31. You can first find the energy, you find the speed, again find the momentum. But if you're a mathematician, you can just play around with those two equations. So from my calculator, I can find P. 2 times 1 point exponent negative 19 times 850 times 9.11 exponent negative 31 square root. So momentum is 1.57 times 10 power negative 23, which is approximately 1.6 times 10 power negative 23 Newton seconds. Calculate the de Broglie wavelength. Of course, de Broglie wavelength is equal to h over the momentum, which is 6.63 times 10 power negative 34, divided by the momentum, 1.6 times 10 power negative 23. So from my calculator, this is 4.1 times 10 power negative 11 as the de Broglie wavelength of that electron. You see that the de Broglie wavelength of the electron is very close to the interatomic spaces. Later on we shall see why electrons undergo diffraction, and electrons can be used in the study of crystal structures because their de Broglie wavelength is almost of the same order as the interatomic space. Okay. Describe an experiment to demonstrate the wave nature of electrons. You may draw a diagram. The wave nature of electrons. The wave nature of electrons is normally demonstrated by electron diffraction. So we are going to demonstrate electron diffraction. I'll try to draw a diagram. I'll draw a diagram which is very easy and simple. You can draw a better diagram, there's no problem. So here I have a filament which is have a cathode which is going to be emitted. Of course, it is going to be the source of electrons. The electrons are going to be emitted there, and they must be accelerated towards a thin layer of graphite. So I will need a screen here. Let me put here a screen inside. I'll put here a screen inside the fluorescent screen, and I will put a thin layer of graphite here. This is a beam, an electron beam tube or a discharge tube. So here I will have a thin layer of graphite. So electrons are going to be produced by thermionic emission, that is hitting the cathode. And let's say a beam of electrons is going to be emitted and directed towards the thin layer of graphite. We need something to accept these electrons, so I'll add an anode here. I'll just add something like an anode somewhere here to accelerate these electrons. So that is my anode. It is going to be responsible for accelerating the electrons. So this is going to be showing beams of electrons. So those are electrons being accelerated towards the graphite film. When the electrons reach the graphite film, because their diffraction, their wavelength is almost the same as interatomic spacing, they pass through the graphite film and undergo diffraction. They form what we call diffraction patterns. So these will form what we call diffraction patterns. So I'll draw some of the diffraction patterns here. Did I draw a vertical line? If the line is not very vertical, let me try to change it. So the electrons are undergoing diffraction and they are going to form diffraction patterns on the screen, which diffraction patterns are actually concentric circles. So these will hit on the screen, of course, because we are seeing this in 2 dimensions, but in class you must have seen this in a discharge tube, and you must have seen what is actually formed on the screen. So what is formed on the screen is what I want to now draw lastly. So if you were to look at the screen, of course, for us inside in 1 dimension, I will just represent the spots with dots here. But if you were to look at what happens inside the screen, you are going to see concentric circles. So the diffraction patterns will be concentric circles. So those are the diffraction patterns. So I'll just name my diagram. Just for simplicity, I'll use a different color. So these ones are the diffraction patterns, which are concentric circles. These are the diffraction patterns. So here we have a fluorescent screen. Of course, this is an evacuated tube, so this is a vacuum. That is a vacuum. So here we have a thin graphite layer or carbon, because graphite is carbon. So that is a thin graphite layer. So here we have the electron beam. Of course, we have the anode here to accelerate the beam, and we have the cathode here. Yeah, so this one, out of 5 marks, I think I have more than 3. I could be having 4 marks here because labeling the drawings showing that the diffraction patterns are concentric circles, showing that the beam has been accelerated, and on the screen, that's what we have. I have exhausted most of the marks, so I will just write a few explanations saying that the diffraction patterns are concentric circles. The diffraction patterns are concentric circles. Concentric circles similar to the diffraction patterns observed with visible light. Similar to diffraction patterns observed with visible light. As simple as that. So if you want to, you can even say that electrons are accelerated through a high speed. The electrons are accelerated through a high speed towards a thin graphite layer, and then the diffraction patterns are concentric circles similar to the diffraction patterns observed with visible light. So there's an anode at a high voltage, so that there's a high potential difference between the cathode and the anode to accelerate these electrons. Okay, I want this video to be 2 hours, so I have 7 minutes. Explain what is meant by a photon, and this time it is 3 marks. So a photon is a packet of energy, a quantum of energy of electromagnetic radiation, a quantum of energy of electromagnetic radiation. A quantum of energy of electromagnetic radiation, and the energy of electromagnetic radiation is equal to Planck constant. Energy is equal to Planck's constant times the frequency. Energy is equal to Planck's constant times the frequency. An emission spectrum is seen as a series of differently colored lines on a black background. Suggest how this observation provides evidence for the discrete energy levels of discrete electron energy levels in atoms. Of course, electrons have specific or occupy specific energy levels. They are telling us different colored lines, meaning each colored line represents a specific wavelength or frequency. Remember, energy is Planck's constant times this frequency. Therefore, if it represents a different frequency, then it represents a different energy, a different photon energy, which means that there are specific energies. There will be specific energy changes between energy levels. That is, we should expect discrete energy levels. So each colored line corresponds to one wavelength. And when I talk about one wavelength, I'm referring to one frequency. Each colored line corresponds to one wavelength or one frequency. Remember, energy is equal to Planck's constant times frequency. Energy equals to Planck's constant times the frequency. Of course, if the lines are separated, the frequencies are not overlapping, the energies are not overlapping. So the energy is equal to Planck's constant times frequency. This implies specific energy change This implies specific energy change between energy levels. Between energy levels. So we can conclude that there are discrete levels. So discrete energy levels. So discrete levels. Because energy is Planck's constant times frequency, and yet each colored line represents one frequency, it means that there are specific energy changes that are possible for electrons. There are specific energy change between energy levels. So discrete energy levels of electrons. Okay. Take what is meant by work function. Work function, of course, now we are familiar with this. The minimum energy of electromagnetic radiation required to remove an electron from a metal surface. That is work function. The variation with the frequency f of the maximum kinetic energy Ek of electrons emitted from the surface of sodium metal is shown here. So we have Ek against frequency. I say the graph is always the same, always a straight line with an x-intercept. Okay, so use the gradient of the graph to determine a value for Planck's constant. They have told us here that photon energy is equal to work function plus maximum kinetic energy. Used the graph with kinetic energy against frequency. So remember HF is equal to HF naught plus Ek, maximum kinetic energy. It is a graph of Ek against F. So you see that the gradient is Planck's constant. So gradient equals to H, Planck's constant, which is going to be equal to, so the gradient, let me find the gradient here. I'll take this point here, which is this one. I can even take this one where it crosses the x-axis, and I'll take this point here. Put it on my ruler to see if it is the point. Yes. So gradient is going to be the change in the y is going to be this is 0 point. The scale here is 0.02. 1, 2, 3, 4, 5, 6, 7. That is 0.14. So which is going to be 0.54 minus 0 on the y-axis. That will be times 1.6 times 10 power negative 19 to change it to joules. Divide by the x-axis. On the x-axis, the scale is 0.5 divided by 10, that is 0.05. So this is 7.1. 7.1 minus, this is 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 6 times 6 times 0.05. 6 times 0.05. 0.3. So that is 5.8. 5.8. And here it is times 10 power 14. So 0.1, I'm on my calculator, 0.4 times 1.6 exponent negative 19 divide by 7.1 minus 5.8 exponent negative 14. So this is giving me 6.65 times 10 power negative 34. So that is the gradient. Therefore, it is going to be my value of h. 6.65 times 10 power negative 34. You can also verify. Okay, lastly, the sodium metal in B has a work function 2.4 times 10 power negative, 2.4 electron volts. The sodium is replaced by calcium, whose work function is 2.9 electron volts. On the figure, draw a line to show the variation with the frequency f of the maximum kinetic energy. So you notice that f is higher. We can find f naught here. F naught is going to be work function divided by h. The work function is now 2.9 times 1.6 times 10 power negative 19 divided by 6.63 times 10 power negative 34. My calculator, 2.9 times 1.6 exponent negative 19 divided by 6.63 exponent negative 34. So this is 6.99 approximately 7.0. 6.998 times 10 power negative power 14, which is approximately 7.0 times 10 power 14 hertz. So it means my graph should go through 7.0 times 10 power 14 hertz and should be, of course, a straight line parallel to the one which is already there. So I have to draw a straight line here. I have to draw a straight line which is parallel to the one which is already there. So it should be at 7.0 as the threshold. So I need a straight line here. So I hope that is a parallel line. So you try to draw a very perfect parallel line, but it is starting from 7.0 because the new work function is the new threshold frequency is 7.0. Okay, so that marks the end of video of part 1. See you in part 2. See you in part 2.